Hey there, how's it going? Thanks for joining me today. Whether you're relaxing at home, on your commute, or winding down for the evening, I'm really glad you're here. October 15th, 2028, 3:17 in the morning, Hawaii Standard Time. While most of the world sleeps, Dr. Sarah Chen sits alone in the control room of the Subaru telescope, perched atop Mauna Kea, a dormant volcano rising 4,200 meters above the Pacific Ocean. She's 6 hours into what should be a routine overnight shift, running automated surveys of the deep sky, cataloging distant galaxies, and hunting for asteroids that might someday threaten Earth. It's work that sounds exciting to outsiders, but often feels like babysitting computers. The telescope does most of the work. Her job is to make sure nothing goes wrong, and occasionally adjust parameters when the software flags something unusual. Before we continue this journey, tell us where you're tuning in from, and if this story resonates with you, make sure you're subscribed, because tomorrow I've saved something extraordinary for you. Chen is fighting exhaustion. She's been awake since 6 the previous morning, and the thin air at this altitude makes everything harder thinking, moving, even staying conscious. Her coffee has gone cold in its ceramic mug, but she drinks it anyway, grimacing at the bitter taste. Outside the control room windows, the universe stretches infinite and indifferent. Thousands of stars burn in the pristine darkness above the cloud layer. Down below, somewhere beyond the volcanic slope, the lights of Hilo glimmer like a small constellation fallen to Earth. Then her screen flashes. A yellow alert box appears over the data stream, accompanied by a soft chime that sounds almost apologetic for interrupting. Chen has seen thousands of these alerts. Usually, they're nothing cosmic rays hitting the detector, satellite streaks, known asteroids passing through the field of view. She's about to click dismiss when something in the preliminary data makes her pause. The parallax calculations look wrong. The apparent motion suggests something much closer than the background stars, but the brightness indicates something large, very large. She sets her coffee mug on the desk and leans forward, suddenly alert despite her exhaustion. Her fingers move across the keyboard, pulling up the raw data feeds and running a quick verification check. The numbers that appear on her screen don't make sense. She runs the calculation again, certain there's been an error in the automatic processing. The telescope has detected an object with an extremely high proper motion, meaning it's moving noticeably against the background stars. But the brightness profile suggests enormous size. These two facts shouldn't coexist. Small objects can move fast across our field of view. Distant galaxies are large but barely move at all over human timescales. But something both large and moving fast, and coming from outside the plane of the solar system where known asteroids orbit. Her coffee mug slips from her fingers. It seems to fall in slow motion, tumbling through the air before shattering on the tile floor in an explosion of ceramic shards and cold coffee. Chen doesn't even notice. Her eyes are locked on the screen where the preliminary trajectory calculation has just completed. The object isn't following any known asteroid trajectory. It's not in an orbit around the Sun at all. The velocity vector points backward, out of the solar system, toward interstellar space, which means it's coming from interstellar space. Here's what's really happening in this moment. Chen has just become the first human being to detect an interstellar visitor since Borisov passed through our solar system in 2017. But unlike Oumuamua in 2017 and Borisov, this object is massive. Not 400 meters like Oumuamua, that first mysterious interstellar visitor that looked more like a giant cigar than any asteroid we'd ever seen. Not even 500 meters like Borisov, the icy comet that wandered in from another star system. The preliminary size calculations, which Chen runs 3 times because she cannot believe what she's seeing, suggest something at least 50 kilometers across. 50 kilometers. To put that in perspective, the asteroid that killed the dinosaurs 66 million years ago was roughly 10 kilometers in diameter. The asteroid Vesta, one of the largest objects in the asteroid belt between Mars and Jupiter, is about 525 kilometers across. What Chen is looking at falls somewhere between catastrophic and planetary in scale. It's larger than the entire island of Oahu, which spreads out in the ocean far below her feet. It's larger than any asteroid that has struck Earth in the last 4 billion years, and it's heading into our solar system at 42 kilometers per second, roughly 150,000 kilometers per hour. Chen's hands are shaking as she initiates the verification protocol. This is the procedure every astronomer dreads and dreams about. Simultaneously, the moment when you think you've discovered something that will change everything. But you need to be absolutely certain before you wake up colleagues around the world and potentially trigger a global panic. She points the telescope to 3 different calibration stars, verifying that the instrument is working correctly. It is. She checks the timing systems, making sure the atomic clocks that timestamp each observation are synchronized. They are. She runs the trajectory calculation using 3 different software packages, including one she wrote herself during her graduate work. All 3 return the same terrifying result. The object has more mass than all the asteroids humanity has ever catalogued combined. The gravitational perturbations she's measuring, the way this thing is subtly affecting the orbits of known objects in the outer solar system, suggest a density consistent with a mixture of rock and ice. And it's not slowing down. When objects fall into the inner solar system from the Oort cloud, that distant sphere of icy debris that surrounds our Sun, they accelerate as solar gravity pulls them in. But this object is coming from outside that gravitational well entirely. Its speed is its own, carried from whatever stellar neighborhood it called home before beginning its lonely journey through the space between stars. Chen realizes she's holding her breath. She forces herself to inhale, then exhale slowly. Her training takes over. First, document everything. She begins creating a data package, raw images, processed images, astrometry measurements, photometry data, the spectroscopic observations from the archive that happened to catch this object before the computer recognized it as anomalous. Everything that will be needed to confirm this discovery independently. As she works, part of her brain is doing the terrifying math. Kinetic energy equals 1/2 mass times velocity squared. This thing has so much energy that if it hit Earth, and her preliminary trajectory suggests it could, the impact would release more energy than every nuclear weapon ever built, exploding simultaneously. More energy than 1,000,000 volcanic eruptions. More energy than the asteroid that created the Chicxulub crater and ended the age of dinosaurs. In those first surreal hours, while the Pacific Ocean sleeps peacefully below the mountain, while billions of humans dream in their beds, unaware that the universe has just served notice, Chen initiates the alert protocol. This is a carefully designed system created specifically for moments like this, though nobody really believed such a moment would come. She sends encrypted messages to the Minor Planet Center in Cambridge, Massachusetts, to the Jet Propulsion Laboratory in Pasadena, California, to the European Space Agency in Germany, to observatories in Chile, South Africa, Australia, China. The messages are terse, professional, carefully worded to convey both urgency and uncertainty. Possible interstellar object detected. Large. Fast. Request immediate follow-up observations. Within 30 minutes, while Chen is still alone in the control room trying to process what she's discovered, the first responses begin arriving. The Gemini North Telescope, just down the mountain from her position, swings toward her coordinates. The Keck telescopes, the largest optical telescopes on Mauna Kea, interrupt their scheduled observations. In Chile, where dawn is breaking, the Very Large Telescope Array pivots to catch the object before it sets below the horizon. The responses are immediate because every astronomer understands what possible interstellar object means. Only 2 have ever been confirmed in all of human history. A third detection would be remarkable. A third detection, described as large and fast, would be world-changing. By the time the sun rises over Hawaii 6 hours later, painting the volcanic landscape in shades of red and gold, every major telescope on Earth has confirmed what Chen discovered. The coordinates she transmitted have become as famous among astronomers as any in human history. The object is real. The size estimates, refined by multiple independent observations, converge on 50 to 55 kilometers across larger than initial calculations suggested. The velocity holds steady at 42 kilometers per second, and the trajectory, calculated with increasing precision as more data arrives, shows the object entering our solar system at an angle that will bring it through the plane where planets orbit. The naming happens quickly, following established protocols. The International Astronomical Union designates it ISO 3, Interstellar Object 3. It's a clinical bureaucratic name that feels absurdly inadequate for something so momentous. But the media, which picks up the story as soon as the scientific community confirms the discovery, needs something more visceral. They call it Goliath. The name spreads across social media within hours. By the end of that first day, ISO 3 has been erased from common usage. Everyone calls it Goliath. The name fits. Biblical. Ominous. A giant that threatens everything. As news breaks across time zones, first in Asia as people wake to morning broadcasts, then in Europe, then in the Americas, humanity experiences something unprecedented in our species' history. 8 billion people, separated by language, culture, religion, politics, and geography, simultaneously look up at the same sky with the same thought. Somewhere up there, beyond Neptune, beyond the orbit of Pluto, something approaches. Something larger than comprehension. Something that makes every disaster movie ever filmed look quaint and naive. Every previous threat, wars, pandemics, climate change, economic collapse, suddenly feels manageable compared to this. Those are problems we created and might solve. Goliath is the universe reminding us that we're very small and very fragile, living on a tiny rock in an infinite darkness that doesn't care if we survive. The last time Earth encountered an object this size moving this fast was approximately 4 billion years ago, during a period astronomers call the Late Heavy Bombardment. Back then, the solar system was still young and chaotic. Jupiter and Saturn were settling into their final orbits, and their gravitational influence scattered countless asteroids and comets throughout the inner solar system. The Moon's face is still scarred by impacts from that ancient violence. Every crater you see when you look up at the full moon is a memorial to a collision that happened when Earth was young and lifeless. But back then, no one was watching. No one was calculating trajectories or measuring velocities. No one was terrified because no one existed to be terrified. The rocks fell in silence, reshaping worlds in an empty system where consciousness had not yet emerged. This time is different. This time, we see death coming from 13 billion kilometers away. We can measure its size, calculate its speed, predict its path. We know with increasing precision exactly when it will arrive in the inner solar system where Earth orbits. The computers at JPL, running continuously now, refining their models with every new observation, show the same result. 7 years, 4 months, and 12 days. That's how long we have. That's how long humanity has to figure out what to do about an interstellar mountain range flying toward us faster than we can quite comprehend. We can't stop it. We probably can't deflect it. But we're going to try anyway, because that's what humans do when faced with the impossible. We fight. We calculate. We hope. We look up at the stars that once seemed so beautiful and distant, and we realize they're neither. The universe is close. The universe is dangerous. And the universe, we're learning, sometimes sends visitors we never expected and definitely didn't want. Dr. Sarah Chen, drinking fresh coffee as the sun rises over Mauna Kea, knows she'll be remembered forever as the person who discovered Goliath. She's not sure that's a legacy anyone would want, but as she watches her colleagues arrive, as the control room fills with voices and urgent activity, as the mountain transforms into the hub of the most important scientific investigation in human history, she allows herself a small moment of wonder. We're so small, she thinks, and we're about to face something so large. But we're not blind anymore. We see it coming. That has to count for something. To grasp what 50 kilometers of rock and ice moving at 42 kilometers per second really means, we need to forget everything Hollywood has taught us about asteroids. This isn't a big space rock that Bruce Willis can blow up with nuclear weapons. This isn't a threat we can punch our way out of with human bravado and last-minute heroics. Goliath is a mountain range flying through space faster than Earth, orbits the Sun, and the physics involved are so extreme they border on incomprehensible. Let's start with size, because our brains aren't good at visualizing cosmic scales. Mount Everest, the tallest mountain on Earth, rises 8,849 meters above sea level. Stack 6 Everests on top of each other, and you're approaching Goliath's height, but that's just one dimension. Goliath is roughly 50 kilometers in every direction, a massive irregular chunk of ancient matter that has been drifting through interstellar space for millions, possibly billions of years. If you placed Goliath next to Manhattan Island, it would cover the entire borough and extend well into Brooklyn and Queens. If you dropped it on Los Angeles, it would stretch from Santa Monica to Pasadena. This is the fascinating part. Objects this large aren't really rocks in any conventional sense. They're more like small worlds, with their own gravity, their own geology, their own history written in layers of accumulated material. Now imagine that entire mass moving at 42 kilometers per second. That's faster than anything humans have ever built. The Parker Solar Probe, humanity's fastest spacecraft, touches 192 kilometers per second at its closest approach to the Sun, but it achieves that speed by falling into the Sun's gravity well. Goliath carries its speed independently, accumulated across interstellar distances. Moving this fast, it could circle Earth's equator 40,075 kilometers in just under 16 minutes. It could travel from New York to London in 2 seconds. The numbers are so extreme they stop feeling real, but here's what makes them terrifying: kinetic energy scales with the square of velocity. Double the speed, quadruple the energy. At 42 kilometers per second, Goliath carries kinetic energy equivalent to roughly 10 billion Tsar bombas. The Tsar bomba, detonated by the Soviet Union in 1961, was the largest nuclear weapon ever built, 50 megatons of destructive force. The shockwave circled Earth 3 times. Windows shattered 900 kilometers away. The mushroom cloud rose 64 kilometers high, piercing the stratosphere. Now multiply that by 10 billion. The numbers become abstract, but the implication is clear. If Goliath strikes Earth, it won't be an extinction-level event. It will be a planet-sterilizing event. The impact would vaporize oceans, liquefy continental crust, and generate enough heat to turn the atmosphere itself into plasma. Earth would glow like a small star for weeks. Life, if anything survived at all, would be reduced to perhaps bacteria deep underground or extremophiles living near hydrothermal vents. Everything else, every tree, every animal, every human, every city, every achievement of civilization would be erased so completely that future geologists, if they existed, would find only a thin layer of shocked quartz and vaporized material marking the moment Earth died. But here's what makes Goliath truly terrifying. Beyond the raw kinetic energy, its gravity. An object this massive doesn't just pass through our solar system like a ship through water, leaving no trace of its passage. It warps the very fabric of space-time around itself. Einstein taught us that mass and energy curve space, and objects moving through that curved space follow paths we perceive as gravity. Picture a trampoline pulled tight. Place a bowling ball in the center, and the fabric sinks, creating a depression. Now roll marbles across the trampoline. They curve toward the bowling ball, following the warped surface. Goliath is the bowling ball, and every asteroid, comet, and planet in our solar system is a marble feeling that curve. The gravitational influence extends surprisingly far. Gravity follows an inverse square law: double the distance, quarter the force. But with an object as massive as Goliath, even weak gravitational tugs matter when applied across millions of kilometers. Computer simulations run at NASA's Jet Propulsion Laboratory show gravitational perturbations affecting known asteroids when Goliath is still 5 billion kilometers away, roughly the distance from the Sun to Pluto. These aren't large effects, not yet, but they're measurable. Asteroid trajectories that have been stable for millions of years show tiny deviations. Comets in highly elliptical orbits experience slight timing changes in their perihelion on their closest approach to the Sunday. The solar system, which seems eternal and unchanging on human timescales, reveals itself to be a delicate clockwork that can be disrupted by sufficiently large intruders. Jupiter becomes the wild card in these calculations. Our solar system's largest planet, containing more than twice the mass of all other planets combined, usually acts as a cosmic vacuum cleaner. Its enormous gravity has spent billions of years sweeping up asteroids and comets that might otherwise threaten Earth. When comet Shoemaker-Levy 9 broke apart and crashed into Jupiter in 1994, astronomers watched impacts that would have devastated Earth leave temporary scars the size of our entire planet in Jupiter's atmosphere. We owe our existence, at least partially, to Jupiter's protective presence. But Jupiter's gravity works both ways. When objects pass through its gravitational sphere of influence at the right angle and velocity, Jupiter doesn't capture them, it accelerates them, flinging them like stones from a cosmic slingshot. The calculations are complex, involving three-body dynamics that strain even modern supercomputers, but the scenarios are clear. If Goliath passes within 600 million kilometers of Jupiter, and current trajectory models suggest it will pass within 400 million kilometers, Jupiter's gravity could slingshot our visitor directly toward the inner solar system. Its cosmic pinball, and Earth might end up in the pocket. The exact deflection depends on dozens of variables: Goliath's precise mass, its velocity vector, the timing of its Jupiter flyby relative to the gas giant's position in its orbit. Change any one factor by a fraction of a percent, and the outcome shifts dramatically, which means as Goliath approaches, as our measurements become more precise, the predicted trajectory will fluctuate. We'll watch probability cones narrow and shift, watching Earth move in and out of danger zones, unable to know our final fate until Goliath has already passed Jupiter and the gravitational die is cast. The composition matters enormously, and this is where Goliath becomes truly strange. Spectroscopic analysis, measuring which wavelengths of sunlight the object reflects or absorbs, reveals something unexpected. Goliath isn't uniform. Its surface shows exposed layers like a cosmic geology textbook, different materials visible in different regions. There's water ice, which appears blue in certain wavelengths. There's methane ice, giving some areas a reddish tint. There are rocky silicates, the same materials that make up terrestrial planets like Earth. And disturbingly, there are traces of heavy metals in concentrations that shouldn't exist in a typical solar system body. Here's what's actually happening. The isotope ratios are wrong. When astronomers analyze the spectroscopic signatures in detail, comparing the abundance of different atomic isotopes in Goliath's surface material to known solar system objects, the numbers don't match. Our solar system formed 4.6 billion years ago from a cloud of gas and dust with a particular mixture of elements. Every asteroid, planet, and comet formed from that same primordial material, so they all share similar isotopic fingerprints, Slight variations, but recognizably related. Goliath's isotope ratios suggest it formed somewhere else, in a stellar environment with different abundances of heavy elements. The ratios particularly point to enrichment in iron-60 and nickel-60, isotopes that form primarily in supernova explosions. This means Goliath likely formed in the heart of a supernova, a stellar explosion so violent it outshines entire galaxies. When stars more than 8 times the mass of our Sun exhaust their nuclear fuel, they collapse catastrophically. The core implodes in less than a second, then rebounds in an explosion that releases more energy in a few minutes than our Sun will produce in its entire 10 billion year lifetime. Temperatures exceed 100 million degrees Celsius. Under these extreme conditions, nuclear fusion creates heavy elements that don't form in normal stellar interiors: gold, platinum, uranium, and the unusual isotopes spectroscopists are detecting in Goliath's spectrum. Whatever star system gave birth to this thing died violently, probably millions of years ago and hundreds of light-years away. Goliath is shrapnel from that stellar corpse, blown outward in the supernova explosion, cooled and solidified during millions of years of interstellar drift. It carries elements that haven't existed in our solar system for billions of years, locked in rock and ice, traveling the vast dark between stars until, by chance or perhaps cosmic inevitability, its lonely orbit intersected with ours. There's something deeply unsettling about this realization. Goliath isn't just a threat, it's a messenger from stellar death, carrying the remains of a murdered sun into our peaceful corner of the galaxy. The magnetic readings add another layer of strangeness. Initial measurements from Earth-based magnetometers detect a weak but definite magnetic field surrounding Goliath. The field strength is comparable to a refrigerator magnet, roughly 50 Gauss at the surface. That sounds weak, and by terrestrial standards it is. Earth's magnetic field is only about half a Gauss at the surface, and it's strong enough to deflect the solar wind and create auroras. But Goliath is 50 kilometers across. A weak field distributed across that much volume represents an enormous amount of stored magnetic energy. The field probably originates from magnetized iron in Goliath's interior, frozen in place when the material solidified billions of years ago. But here's the critical part. Goliath will pass through regions of space filled with charged particles. The solar wind, a constant stream of electrons and protons flowing outward from the Sun, will interact with that magnetic field. When charged particles encounter magnetic fields, they spiral along field lines, creating electric currents. Those currents generate their own magnetic fields, which can amplify the original field in a feedback process. As Goliath penetrates deeper into the inner solar system, approaching regions where the solar wind is denser, these electromagnetic effects could trigger auroras visible from Earth even before closest approach. The sky might glow with shimmering curtains of light at the equator, something that normally only happens near the poles. It would be beautiful, a final light show before potential annihilation. The electromagnetic effects could also damage satellites. Modern civilization relies on thousands of satellites for communication, navigation, weather forecasting, and military operations. These satellites are designed to withstand normal space weather, solar flares, geomagnetic storms, the usual hazards of operating in orbit. But Goliath's approach will create abnormal conditions. The interaction between its magnetic field and the solar wind could generate powerful electromagnetic pulses, surges of radio waves that could fry sensitive electronics. GPS satellites might fail. Communication networks could go dark. Weather satellites might stop transmitting. Even if Goliath misses Earth entirely, even if the gravitational deflection saves us from direct impact, we might still face a technological apocalypse, all our orbital infrastructure destroyed, knocked back to an era before satellite technology existed. The tumbling adds a final complication. As observations accumulate and astronomers track Goliath night after night, a pattern emerges in the brightness variations. The object isn't spherical. Spectroscopic data suggests an irregular, roughly ellipsoidal shape, and it's rotating. Every 17 hours and 36 minutes, it completes one full rotation around its axis. This tumbling motion, probably initiated by some ancient collision billions of years ago, means different faces are exposed to solar heating as Goliath approaches the Sunday. Ice on the sunny side sublimates, creating jets of gas that act like natural rocket engines, subtly changing the trajectory in unpredictable ways. Any deflection attempt would need to account for this. Tumbling, we can't just aim at a stationary target. The surface we need to hit keeps moving, and the object's center of mass shifts slightly with each rotation as internal ice sublimates and refreezes. It's like trying to shoot a tumbling football from a moving car, while the football is the size of a mountain and moving at speeds that make bullets look stationary. This is what we're facing. Not a simple rock we can blow up with nuclear weapons, not a predictable threat that follows neat equations. Goliath is a complex, massive, magnetized, tumbling world killer carrying materials forged in stellar death, warping space-time as it approaches, threatening to destabilize everything in its path through sheer gravitational presence. And we have 7 years to figure out how to survive its passage. The physics are terrifying. The uncertainties are worse. But understanding what we're facing is the first step toward fighting back. We can't defeat physics, but maybe, just maybe, we can work with physics to nudge this cosmic pheasant, intruder, onto a safer path. The question isn't whether we understand the threat we do, with increasing and horrible clarity. The question is whether understanding is enough. The moment Goliath's trajectory is confirmed, not just detected, but verified by multiple independent observatories across the globe, humanity transforms overnight. It's not gradual. It's not a slow dawning of realization. Within 72 hours of Dr. Chen's discovery, the United Nations Security Council convenes in the most important session in its 83-year history. The chamber in New York, normally a theatre for diplomatic posturing and carefully worded statements that mean nothing, becomes the command center for species survival. Representatives from nations that have spent decades in bitter opposition suddenly find themselves on the same side of an argument nobody wants to be having. China moves first, and the move is shocking. The People's Republic has spent decades guarding its technological secrets, maintaining strict controls over information about its space program and military capabilities. But on day 4 after Goliath's detection, at an emergency session broadcast globally, the Chinese representative stands and releases classified plans for nuclear pulse propulsion systems they've been developing since 2021. These aren't theoretical designs. These are working blueprints for spacecraft that ride the shockwaves of nuclear explosions, using atomic bombs as propellant to achieve velocities impossible with conventional rockets. The technology was pioneered by American physicists in the 1950s with Project Orion, but China has refined it, modernized it, made it practical. They offer this technology freely to the world. No strings attached, no demands for reciprocity. Russia follows within hours. The foreign minister, speaking from Moscow via video link, makes an admission that causes audible gasps in the Security Council chamber. Russia admits to maintaining a stockpile of 150 megaton nuclear devices, weapons far larger than anything publicly acknowledged, ostensibly for asteroid deflection purposes. These weapons, each roughly 3 times more powerful than the Tsar Bomba, have been kept in secret facilities in Siberia for decades. The revelation violates multiple nuclear treaties, and under normal circumstances would trigger international condemnation and sanctions. But these aren't normal circumstances. The world doesn't condemn Russia. The world asks how quickly those weapons can be deployed. The United States activates something called Project Longshot, and even veteran Washington observers are caught off guard. Longshot is a black-budget program that apparently began during the Obama administration, continued through multiple presidencies without public disclosure, and involves nothing less than turning the entire asteroid belt into ammunition. The concept is audacious. Use automated mining spacecraft to capture small asteroids, perhaps 5 to 10 meters across, and equip them with guidance systems and propulsion units. Create a swarm of kinetic impactors that can be precisely directed at incoming threats. The technology has been in development for 15 years, hidden in classified annexes of defense budgets, disguised as research into asteroid mining for commercial purposes. Now it's revealed as a planetary defense system that could, theoretically, hurl hundreds of asteroids at Goliath in coordinated waves. Here's what's actually happening in these first frantic weeks. Every petty border dispute, every trade war, every territorial squabble, every ideological conflict that seemed so important just days ago evaporates like morning mist under a hot sun. Kurdish independence, the Kashmir conflict, the South China Sea territorial disputes, Brexit complications, trade tariffs, sanctions, regimes, all of it becomes instantly, obviously irrelevant. When faced with extinction, humans discover they can cooperate after all. It's almost funny, in a dark way. We needed a cosmic threat to remind us we're all on the same fragile rock, breathing the same thin atmosphere, orbiting the same yellow star in a universe that doesn't care about our differences. The detection network expands exponentially, and this expansion happens with a speed that would be impossible under normal bureaucratic timelines. The James Webb Space Telescope, humanity's premier observatory for studying the early universe, abandons all other observations. Every second of observation time, previously scheduled years in advance and allocated to competing research teams through rigorous peer review, is redirected to track Goliath continuously. SpaceX, responding to direct requests from NASA and the European Space Agency, launches 17 Starship rockets in 30 days, a launch cadence that shatters all previous records. Each Starship carries components for a massive radio telescope array being assembled at Earth's L4 Lagrange point, one of the gravitationally stable locations where the gravitational pulls of Earth and the Sun balance perfectly. China's Tiangong space station, originally designed for scientific research and national prestige, is converted into a dedicated Goliath observation post. Modules intended for materials science experiments are retrofitted with high-resolution telescopes and spectrometers. The 3-person crew is replaced with 7 specialists in orbital mechanics and astrometry. The station becomes a permanent eye in the sky, never blinking, tracking Goliath through every orbit. But perhaps the most remarkable development is grassroots. Amateur astronomers worldwide, equipped with increasingly sophisticated equipment that would have been considered professional grade just decades ago, form something called the Goliath Watch Network. These aren't casual stargazers with backyard telescopes. These are serious observers with CCDs, with computerized mounts, with spectroscopic capabilities, with the skills to contribute meaningful data. A teenager in Argentina, a retired engineer in Japan, a university student in Nigeria, a farmer in Kansas. They coordinate through open-source software, divide the sky into sectors, provide round-the-clock coverage that no government agency could achieve alone. When weather closes observatories in the Northern Hemisphere, the Southern Hemisphere picks up the watch. When technical failures temporarily blind a major facility, amateurs fill the gap. A 12-year-old girl in Mumbai named Priya Sharma writes an algorithm that improves trajectory prediction accuracy by 3%. She's not a prodigy in the traditional sense, not some unrealistic genius who understands physics beyond her years. She's just a kid who's good at math and spends her time playing with orbit simulation software as a hobby. She notices that the existing prediction algorithms don't account for solar wind pressure variations across Goliath's large surface area. It's a small effect, But at interstellar distances, small effects accumulate. Her algorithm, written in Python and posted to an open-source repository, is noticed by a graduate student who shows it to a professor who contacts JPL. Within a week, Sharma's correction is implemented in the official trajectory calculations. She appears on morning news shows, slightly bewildered by the attention, still processing the fact that her hobby just contributed to saving the world. By month 2, humanity has more observational capacity focused on one object than we've ever directed at anything in history. Goliath is watched continuously by instruments operating across the entire electromagnetic spectrum: visible light, infrared, ultraviolet, radio waves, even attempts to detect gravitational waves from its passage through space. Every observation is immediately uploaded to servers accessible to scientists worldwide. The data is open, transparent, analyzed by thousands of experts and millions of amateurs simultaneously. If there's something unusual, if there's a trajectory change, if there's any new information, the entire human species knows within minutes. The data reveals both hope and horror in equal measure. The hope comes from increasingly precise trajectory calculations. Goliath will definitely pass through the asteroid belt, that much is certain. But the exact path through the belt, the timing of the Jupiter encounter, and the final trajectory toward the inner solar system depend on variables we're still measuring. Every new observation narrows the probability cone slightly. We watch Earth's fate oscillate between safe and catastrophic, between a distant past that will merely terrify us and a direct impact that will end us. The uncertainty is psychologically exhausting for the scientists tracking these probabilities, watching numbers fluctuate, knowing that each decimal place represents the difference between survival and extinction. The horror comes from the gravitational chaos Goliath will inevitably trigger. Computer simulations, run on every supercomputer on Earth in America, China, Europe, Japan, India, show the same result with minor variations. When Goliath passes through the asteroid belt, specifically through a region called the Kirkwood Gaps, where asteroid density is highest, at minimum 400 asteroids will be gravitationally scattered. These aren't small rocks. We're talking about objects ranging from 100 meters to several kilometers across, each one massive enough to cause regional or global catastrophes if they hit Earth. Most of these scattered asteroids will be flung harmlessly into deep space or deflected toward the Sun, where they'll eventually either impact the solar surface or be torn apart by tidal forces. But the simulations consistently predict that between 17 and 23 asteroids will be redirected toward Earth's orbital path. Not immediately. These won't arrive for years, even decades after Goliath's passage. We'll face a shotgun blast of threats spread across time. Even if we somehow survive Goliath itself, we'll spend the next century playing cosmic whack-a-mole with multi-kilometer asteroids that have been knocked from stable orbits that have persisted since the solar system's formation. It's the gift that keeps on giving, in the worst possible way. Defeating Goliath becomes only the first challenge. We'll need to maintain the detection network, the defense capabilities, the international cooperation for generations. One catastrophe we might survive through desperate innovation and luck, but dozens of catastrophes stretched across decades. That requires sustained effort, maintained infrastructure, continued funding and attention after the immediate crisis passes. Human civilization has never been good at maintaining vigilance against rare threats. We're reactive, not proactive. We respond to immediate dangers and grow complacent when threats recede. Goliath will test whether we can overcome that tendency. The simulations reveal another unsettling detail. Goliath is tumbling, as discussed earlier, rotating every 17 hours and 36 minutes. But the rotation isn't stable. As Goliath approaches the Sun, solar heating causes surface ice to sublimate, transforming directly from solid to gas without becoming liquid. These gas jets create tiny thrust forces, barely measurable individually but significant in aggregate. The jets are stronger on some parts of Goliath's surface than others because the composition isn't uniform. The differential heating and outgassing creates a net torque, gradually changing Goliath's rotation rate. By the time it reaches the inner solar system, it might be spinning faster or slower, and the axis of rotation might have precessed shifted like a wobbling top. This matters enormously for any deflection attempt. To change Goliath's trajectory, we need to apply force at specific locations and specific times. But if we don't know exactly how the object is rotating, if the rotation is changing in unpredictable ways, then our targeting calculations become uncertain. Imagine trying to thread a needle while wearing thick gloves, in the dark, while someone randomly rotates the needle. That's the challenge. Every deflection strategy, nuclear weapons, kinetic impactors, gravity tractors, solar sails, whatever we attempt must account for this tumbling, and the tumbling itself is only partially predictable. The international scientific community establishes something called the Goliath Consortium, a collaborative framework that supersedes normal academic competition and national rivalries. Research findings are shared immediately, without the usual delays of peer review and publication. Scientists who would normally compete for grants and prestige work together, contributing to shared models and shared understanding. The consortium establishes working groups for trajectory prediction, composition analysis, deflection strategies, impact mitigation, and post-crisis recovery planning. Thousands of researchers contribute, their names listed on a shared digital monument that will either commemorate humanity's finest hour or serve as a memorial to a species that saw extinction coming and tried to stop it. The monitoring reveals subtle changes as months pass. Goliath's brightness fluctuates slightly as different surface materials rotate into view. The spectroscopic signature shifts subtly as solar heating begins to affect the surface chemistry. Outgassing rates increase as Goliath approaches, and solar radiation intensity grows. Each change is analyzed exhaustively, compared against models, used to refine predictions. The object that was mysterious and unknown becomes gradually less so. We learn its secrets, catalogue its properties, understand its nature. Knowledge doesn't make it less dangerous, but knowledge gives us something precious, the ability to plan, to predict, to prepare. Ignorance would be more terrifying than any fact we uncover. By the end of the first year, the detection phase transitions into the response phase. We know where Goliath is, we know where it's going, we know approximately when it will arrive and what damage it could cause. Now comes the harder question. What do we do about it? The answer will require everything. Human civilization has built all our technology, all our science, all our capacity for cooperation and innovation. And even then, it might not be enough. As Goliath crosses Neptune's orbit in year 3 of its approach, the outer solar system begins to dance. This is when the theoretical becomes observable, when computer predictions transform into reality captured by telescopes and spacecraft. Neptune itself, 30,000 times more massive than Goliath, barely notices the visitor. The 8th planet continues its stately orbit, taking 165 Earth years to circle the Sun, largely unperturbed by the interloper passing through its domain. But Neptune's smaller moons tell a very different story, and it's in their orbital changes that we first witness Goliath's gravitational reach. Nereid, Neptune's 3rd largest moon, orbits the ice giant in an extremely eccentric path that takes it from 1,400,000 kilometers at closest approach to 9,623,000 kilometers at its farthest point. Astronomers have always known Nereid's orbit was unusual, probably the result of ancient gravitational encounters, but Nereid's orbit, while strange, has been stable for millions of years, until Goliath arrives. As the interstellar visitor passes within 200 million kilometers of Neptune, Nereid receives a gravitational kick, a tiny acceleration that changes its velocity by just 2 meters per second. 2 meters per second sounds negligible, A human can run faster than that. But in orbital mechanics, small velocity changes compound over time. The calculations performed at the Jet Propulsion Laboratory are definitive. Nereid's new trajectory will gradually become more eccentric over the next several centuries, the orbit stretching like pulled taffy until finally, approximately 800 years from now, Nereid will reach escape velocity and be ejected from Neptune's system entirely. It becomes the first casualty of Goliath's passage. A moon-turned rogue, destined to wander the outer darkness forever. A tiny world condemned to eternal solitude because it happened to be in the wrong place at the wrong time. Astronomers watch this happen in real time, tracking the orbital changes, knowing they're witnessing the destruction of a world that has orbited Neptune since the solar system's formation. Neptune's rings, usually invisible from Earth and barely detectable even by spacecraft, light up as Goliath's gravity triggers collisions among ring particles. The rings are composed of microscopic ice particles and dust, held in delicate balance by Neptune's gravity and the gravitational shepherding of small moons. Goliath's passage disrupts that balance. Ring particles collide more frequently, fragments grinding against each other, generating heat from friction and releasing clouds of gas and dust. The rings temporarily brighten by a factor of 10, becoming visible through amateur telescopes on Earth, a light show 45 times farther from the Sun than Earth, visible across 4.5 billion kilometers of space. The sight is beautiful and deeply unsettling, a reminder that Goliath's influence extends far beyond direct physical contact. But the real chaos begins at Jupiter. The gas giant, positioned unfortunately along Goliath's trajectory, becomes the focus of intense observation as the interstellar visitor approaches. Jupiter is the solar system's kingmaker and protector, its gravity dominating everything within 800 million kilometers. Objects that pass Jupiter can be captured, ejected from the solar system entirely, or most dangerously accelerated toward the inner planets. Everything depends on the approach angle, velocity, and timing. Teams of scientists work continuously, refining calculations, watching as probability cones shift and fluctuate. As Goliath approaches within 500 million kilometers of Jupiter, something unprecedented begins to happen. Jupiter develops a new storm. The planet's atmosphere, a turbulent hell of hydrogen and helium lashed by winds exceeding 600 kilometers per hour, is constantly generating and destroying storms. The Great Red Spot, a hurricane larger than Earth that has raged for at least 350 years, is Jupiter's most famous feature. But as Goliath's gravity begins to tug on Jupiter's atmosphere, creating tidal forces that pull the gas layers in directions they don't normally experience, atmospheric dynamics shift. A new cyclone forms in Jupiter's southern hemisphere, growing rapidly from a small disturbance to a massive storm system half the size of Earth within just 6 weeks. The storm, which astronomers name the Goliath cyclone, becomes one of the most studied weather phenomena in history. Every telescope that can observe Jupiter tracks the storm's evolution. The cyclone rotates counterclockwise, winds at its edge reaching 840 kilometers per hour. Lightning flashes visible from Earth illuminate clouds of ammonia ice crystals. The storm's dynamics are driven partly by internal heat from Jupiter's core and partly by the external tidal stresses imposed by Goliath's gravity. It's a hybrid phenomenon, something that couldn't exist without the unusual circumstances of Goliath's passage. The storm will persist for decades after Goliath leaves, a permanent reminder of this cosmic encounter. The Great Red Spot itself, stable for centuries, begins to elongate and show signs of breaking apart. The spot is an anticyclonic storm. It rotates clockwise in Jupiter's southern hemisphere. As the Goliath cyclone forms nearby, the two storm systems interact through their magnetic fields and wind patterns. The red spot, which has slowly been shrinking for the past century, loses structural coherence. Its edges blur. The characteristic red color, caused by complex photochemistry in Jupiter's upper atmosphere, begins to fade in some regions. Scientists watch anxiously, uncertain whether the Great Red Spot will survive this gravitational disruption, or whether Goliath's passage will end a storm that predates human civilization. Europa, Jupiter's fourth largest moon and one of the most intriguing objects in the solar system, experiences its own crisis. Europa is covered in water ice, smooth and bright, crisscrossed with brown-red cracks that look like veins on pale skin. Beneath the ice lies an ocean of liquid water, kept warm by tidal heating, the gravitational flexing Europa experiences as it orbits Jupiter. This ocean might harbor life, microbial organisms surviving in the lightless depths, feeding on chemical energy from hydrothermal vents. It's one of the best candidates for extraterrestrial life in our solar system, and thousands of scientists have dreamed of sending a mission to drill through the ice and explore that hidden ocean. Goliath's gravity intensifies the tidal heating dramatically. As the interstellar object passes within 400 million kilometers of Jupiter, Europa feels gravitational pulls from both the gas giant and the visitor simultaneously. The ice shell, normally 10 to 15 kilometers thick, cracks like an eggshell. Long fissures open across Europa's surface, some extending hundreds of kilometers. Geysers of water vapor shoot 200 kilometers into space, far higher than any previously observed by spacecraft that have visited the Jupiter system. The geysers freeze almost immediately in the vacuum of space, creating a temporary ring of ice, crystals around Jupiter. For the first time in history, we can directly sample Europa's ocean without drilling through kilometers of ice. Spacecraft already in the Jupiter system, originally sent for other purposes, divert to fly through the geyser plumes. Instruments analyze the composition of the water vapor, searching for organic molecules, salts, dissolved gases, anything that might tell us about conditions in the hidden ocean below. The discovery of complex organic molecules, amino acids and nucleobases, chemicals essential for life as we know it, would normally be the scientific discovery of the century. Headlines would proclaim humanity's first detection of potential extraterrestrial biochemistry. But now, with Goliath bearing down on Earth, Europa's life signs are barely a footnote in news coverage. We might have found evidence of alien life, and hardly anyone cares because we're too busy trying to ensure our own life survives. The asteroid belt transforms into a shooting gallery as Goliath plows through this region of space between Mars and Jupiter, populated by millions of rocky remnants from the solar system's formation. Its gravity acts like an invisible hand, flinging space rocks in all directions. The belt isn't densely packed the way science fiction depicts. You could fly through it blindfolded and probably never hit anything. The average distance between asteroids is measured in hundreds of thousands or millions of kilometers, but there are so many asteroids spread across such an enormous volume that even small probability events become certainties when multiplied by millions of opportunities. Computer simulations predicted 400 asteroids would be significantly perturbed. The actual number, as Goliath passes through during month 41 of its approach, turns out to be 417. Each one represents a potential future threat. A trajectory that has been stable for 4 billion years, suddenly changed, redirected into new orbits that will intersect paths they've never crossed before. Most are small, just tens of meters across, dangerous only to satellites or local regions if they hit Earth. But 23 are larger than 1 kilometer in diameter. These are civilization enders if they strike populated continents. Ceres, the largest object in the asteroid belt and technically classified as a dwarf planet, experiences its first recorded earthquake, or rather, Ceresquake. Ceres is 940 kilometers in diameter, roughly one-third the size of Earth's moon, with a rocky core surrounded by a thick mantle of water ice and a thin, dusty crust. The Dawn spacecraft orbited Ceres from 2015 to 2018, mapping its surface in exquisite detail before running out of fuel. That dead spacecraft, still in orbit, its cameras and instruments silent, witnesses something no human-made instrument has ever recorded: Ceres shaking. The gravitational tidal forces from Goliath's close passage within 30 million kilometers stress Ceres's interior. The ice mantle flexes slightly, just a few meters of movement, but that's enough. A fault line that has existed beneath Ceres's surface since some ancient impact fractures. Seismic waves propagate through the dwarf planet's interior. Surface features shift slightly. The mysterious bright spots in Ocata crater, deposits of salt left by ancient water seepage, crack and release small clouds of vapor. And the Dawn spacecraft, orbiting peacefully for a decade, is finally knocked from its orbit by the vibrations transmitted through Ceres's gravity field. It tumbles away into space, its mission complete, its final observation witnessing Ceres's moment of trauma. Vesta, the second largest asteroid, roughly 525 kilometers across, splits along an existing fault line. Vesta has always been unusual. One entire hemisphere is dominated by an enormous impact crater called Ray Sylvia, created when something massive struck Vesta, roughly 1 billion years ago. That ancient impact created fractures that penetrate deep into Vesta's interior, weaknesses that have persisted across geological timescales. Goliath's tidal forces exploit those weaknesses. The fractures propagate, widening from microscopic cracks into chasms kilometers wide. Vesta breaks into two large fragments, each several hundred kilometers across, plus millions of smaller pieces ranging from boulders to dust. The breakup happens over the course of 3 days. Ground-based telescopes watch Vesta's brightness fluctuate as the asteroid comes apart. First, a sudden brightening as fresh internal material is exposed to sunlight. Then, the light curve becomes chaotic as fragments tumble independently, each one reflecting sunlight at different angles. Within a week, Vesta has transformed from one object into a loose cluster of debris, fragments held together weakly by their mutual gravity but slowly drifting apart. Over the next century, these fragments will spread along Vesta's original orbit, creating a debris field that will become a navigation hazard for any spacecraft traveling through that region. The asteroid belt, stable for 4 billion years since the solar system's formation, when these rocks failed to coalesce into a planet because Jupiter's gravity prevented their accumulation, is permanently altered in a matter of weeks. The neat orbital families that astronomers have catalogued, asteroids grouped by similar trajectories and compositions that indicate common origins, are scrambled. Objects that have never been near each other suddenly find themselves on intersecting paths. Collision rates in the belt increase by a factor of 5, each collision creating more fragments, more debris, more potential hazards. Earth's meteor rates increase 17-fold as debris spreads throughout the inner solar system. Before Goliath, Earth collected approximately 17,000 tons of space dust and small meteoroids annually, most burning up harmlessly in the atmosphere as shooting stars. Now that rate jumps to nearly 300,000 tons per year. Every night becomes a meteor shower. The sky lights up with streaks of burning rock, beautiful and ominous. Astronomers who once looked forward to annual meteor showers, the Perseids, the Leonids, predictable events marking specific times of year, now see meteors constantly. The spectacle loses its wonder and becomes merely background reality, like clouds or stars. Insurance companies collapse worldwide as satellite operators file claims for collision damage. The carefully tracked objects in Earth orbit, monitored by space surveillance networks to prevent collisions, become impossible to track comprehensively as the population of debris increases. Satellites are designed to perform occasional collision avoidance maneuvers, small thruster burns that shift their orbits slightly to dodge predicted close approaches. But when the number of close approaches increases by an order of magnitude, when debris comes from unexpected directions at unexpected velocities, avoidance becomes impossible. Satellites are damaged or destroyed at increasing rates, Communication networks experience outages. GPS accuracy degrades as satellites fail, and replacements can't be launched fast enough. The International Space Station, humanity's outpost in low Earth orbit, is evacuated after 14 near misses in a single day. The station, assembled over decades through contributions from 15 nations, has been continuously inhabited since the year 2000, nearly 3 decades of human presence in space. But as Goliath's gravitational disruption shakes loose debris throughout the solar system, the station becomes too dangerous to occupy. On day 73 of the asteroid belt passage, mission controllers make the painful decision to bring the crew home. 6 astronauts and cosmonauts board their docked spacecraft and undock for the final time, looking back at the station through their windows as they depart. The station continues orbiting empty, its lights still on, its systems still functioning, but no human voices echo through its modules. Eventually, perhaps, when the debris environment improves, humanity will return, but for now, orbital space is too hazardous. Space, once empty and safe, or at least predictably dangerous, becomes a lethal obstacle course. The launch industry experiences its worst year in history as rockets are damaged by debris during ascent. 3 cargo missions to resupply lunar bases are destroyed in the first 50 kilometers of flight, struck by fragments too small to track but large enough to penetrate aluminum hulls. The cost of space access increases dramatically as launch providers add armor to their vehicles, reducing payload capacity to accommodate shielding. Some experts suggest abandoning space operations entirely until the debris clears, a process that might take decades or centuries. But others argue that abandoning space now, just when we need orbital infrastructure to track and respond to threats, would be suicidal. The debate rages in government chambers and corporate boardrooms, while debris continues to rain down. The psychological impact of watching the solar system's architecture collapse in real time is profound. Humans have always taken comfort in the stability of the heavens. The planets follow predictable paths. Eclipses can be calculated centuries in advance. The stars appear fixed in their positions. This celestial clockwork has seemed eternal, operating according to immutable laws that transcend human affairs. But Goliath reveals that stability as illusion. The solar system isn't a perfect mechanism running forever unchanged. It's a dynamic, chaotic system where small perturbations can cascade into large effects. We're watching fundamental transformation happen not over millions of years but over months. The heavens we thought we knew are being remade before our eyes, and we're powerless to stop it. We can only watch, measure, document, and hope that when the chaos subsides, Earth will still be here, and we'll still be on it. Year 4 brings the most ambitious engineering projects in human history. The detection phase is complete. The observation phase continues but has become routine. Now comes the response phase, the desperate, audacious attempt to change Goliath's trajectory enough to save Earth. Every space-capable nation contributes proposals, and the sheer scale of human imagination under existential pressure is remarkable. Some plans are refinements of existing technology. Others push the boundaries of physics. A few border on science fiction, but all share a common thread. They represent humanity refusing to accept extinction quietly. Project Hammer emerges from a collaboration between NASA, the European Space Agency, and Japan's JAXA. The concept is elegantly simple. Use kinetic energy to deflect Goliath by slamming something massive into it at high velocity. But the challenge lies in finding something massive enough to matter. Conventional spacecraft are too small. Even if we built the largest rocket ever designed and crashed it into Goliath at maximum speed, the effect would be negligible, like throwing a grain of sand at a freight train. We need something with real mass. The solution comes from an unlikely source, Apophis. Apophis is an asteroid that terrified astronomers when it was discovered in 2004. Initial trajectory calculations suggested a possible Earth impact in 2029, with odds reaching an alarming 2.7% high, enough to trigger serious concern. Further observations refined the trajectory and eliminated the impact risk, but Apophis remained on watch lists as an object that passes uncomfortably close to Earth. Now, ironically, this former threat becomes our weapon. Apophis measures roughly 70 meters across, and has a mass of approximately 61 billion kilograms. It's not large by asteroid standards, but it's massive compared to anything humans could launch from Earth. The plan involves sending a flotilla of spacecraft to Apophis, equipping the asteroid with ion drives and gravity assist trajectories that will redirect it toward Goliath. The timing is critical. Apophis must arrive at the interception point traveling at maximum velocity, which means using Jupiter for a gravitational slingshot. The calculations are enormously complex, requiring precise coordination across years of careful maneuvering. But if successful, Apophis will slam into Goliath at a combined closing velocity of 80 kilometers per second, nearly twice Goliath's own speed. The impact will be visible from Earth with the naked eye, a flash of light in the night sky, marking the most violent collision in the inner solar system since the late heavy bombardment. Engineers from a dozen nations work on the guidance systems. The spacecraft attached to Apophis must survive years in deep space, operate reliably in extreme cold, and execute burn sequences with microsecond precision. There's no margin for error. If Apophis misses Goliath by even a few kilometers, years of effort and billions of dollars will be wasted. And we only get one shot. There's no time to redirect Apophis again if the first attempt fails. China and India, setting aside decades of border tensions and strategic rivalry, collaborate on Project Mirror. The concept emerged from solar sail research using sunlight pressure as propulsion, but instead of pushing spacecraft, why not use concentrated sunlight to push Goliath itself? The plan calls for launching 10,000 satellites, each equipped with reflective surfaces 50 meters across. These mirrors will position themselves in a carefully calculated formation, focusing sunlight onto specific points on Goliath's surface. The concentrated light will heat surface ice to hundreds of degrees Celsius, causing it to sublimate rapidly and create jets of gas that act like natural rocket engines. The engineering challenges are immense. Each satellite must maintain its position with extraordinary precision, compensating for solar wind, gravitational perturbations, and the tendency of large reflective surfaces to be pushed around by photon pressure. The satellites must communicate constantly, adjusting their positions in real time to keep the focused beam centered on the target area, despite Goliath's rotation. And the system must operate continuously for months to generate sufficient thrust. But computer simulations suggest Project Mirror could deflect Goliath by several thousandths of a degree. Not much, but possibly enough when combined with other efforts. The satellite production becomes a marvel of industrial coordination. Manufacturing facilities in China, India, South Korea, Taiwan, and Vietnam produce components around the clock. The satellites are designed for mass production, sacrificing sophisticated features for simplicity and reliability. Each one is essentially a large mirror with basic station-keeping thrusters, solar panels for power, and a simple computer running pre-programmed positioning algorithms. They're launched in batches of 50 aboard heavy-lift rockets, deployed like seeds scattered by the wind, then left to automatically form their formation. It's the largest artificial structure ever built in space, 10,000 independent objects working as a single coordinated system. Russia's Project Tsar takes a more direct approach: detonate nuclear weapons in Goliath's path. Not on Goliath itself, which would be unlikely to change the trajectory significantly, but ahead of it, creating clouds of debris that would gradually slow the interstellar visitor through millions of tiny impacts. It's like cosmic sandpaper, friction applied over enormous distances. The Russian stockpile of 150 megaton weapons, designed for asteroid defense but now revealed to the world, will be detonated in carefully timed sequence as Goliath approaches. Each explosion will create a rapidly expanding sphere of plasma and vaporized debris. Goliath will punch through these spheres, and while each individual impact is insignificant, the cumulative effect might deflect the trajectory measurably. The plan requires extraordinary precision in timing. The weapons must be placed exactly where Goliath will be, accounting for the object's speed, trajectory, and rotation. Miss by even a few seconds, and the debris cloud will have expanded and dispersed, becoming too tenuous to matter. The Russians develop a system of automated deployment vehicles, essentially ballistic missiles modified for space operation, each carrying a multi-megaton warhead. The vehicles will launch from Plesetsk Cosmodrome in northern Russia, accelerate to interplanetary space, position themselves along Goliath's predicted path, and wait. When the time comes, ground controllers will send the detonation command, and the weapons will explode in a carefully choreographed sequence designed to maximize cumulative deflection. But the most audacious plan comes from an unexpected source, a consortium of African nations led by Nigeria. Project Slingshot would use Earth itself as a gravitational weapon. Here's how it works. Goliath will pass close to Earth regardless of which trajectory it follows. That close passage creates a gravitational interaction that affects both Earth and Goliath. Normally, we'd want to minimize Earth's deflection and maximize Goliath's, but Project Slingshot suggests doing something radical, slightly alter Earth's orbit to maximize the gravitational deflection effect on Goliath while keeping Earth safe. The proposal initially sounds insane. Move Earth's orbit? The planet masses 5.97 times 10 to the 24th power kilograms. Nothing we possess can move something that massive. But here's the insight. We don't need to move Earth much. Just a few thousand kilometers difference in Earth's position at the moment of Goliath's closest approach could dramatically change the gravitational interaction. And while we can't push Earth directly, we can use controlled nuclear detonations in space to very slightly alter Earth's orbital velocity. Accelerate Earth by just a few centimeters per second at the right point in its orbit, and Earth's position months later will be significantly different. The mathematics are verified by teams in Geneva, Tokyo, and Pasadena. It works. It's possible. The precision required is extraordinary. The timing of detonations must be perfect. The yield of each explosion exactly calibrated. The positions in Earth's orbit where they occur optimized through supercomputer simulations. But if executed correctly, Project Slingshot could deflect Goliath by up to 1/100th of a degree while Earth's orbit remains safely within its normal variation range. The long-term effects on climate and seasons would be negligible, less than the natural variations Earth experiences over centuries. Every plan has opponents and proponents, leading to the most important debate in human history. The United Nations forms a Planetary Defense Coordination Committee, bringing together representatives from every nation with space capability and every major scientific institution. The meetings are contentious. Engineers who have devoted years to their pet projects defend them passionately. Scientists point out flaws and limitations. Politicians worry about costs and national prestige. But underneath the arguments, everyone understands the stakes. This isn't about who gets credit for saving Earth. This is about whether Earth survives at all. The crucial question: do we try everything at once, risking interference between methods, or do we bet everything on one approach? Project Hammer's kinetic impact might destabilize Goliath's rotation, making Project Mirror's focused sunlight harder to aim. Project Tsar's nuclear debris clouds might interfere with Project Hammer's trajectory. Project Slingshot's Earth orbital adjustment must be timed perfectly relative to the other efforts. The interactions are complex, the simulations uncertain, but time is running out, and consensus emerges around a coordinated multi-method approach. We'll try everything, carefully sequenced to minimize interference and maximize cumulative effect. If any single method fails, perhaps the others will compensate. It's redundancy born of desperation, but it's our best shot. Meanwhile, as humanity prepares its cosmic defense, preparations for potential failure proceed in parallel. Bunkers are built on a scale that dwarfs anything from the Cold War. The Norwegian Seed Vault, originally designed to preserve crop diversity in case of agricultural catastrophe, is expanded into a small underground city capable of housing 10,000 people for decades. The vault, located on Spitsbergen Island in the Arctic, is carved deeper into the permafrost. Living quarters, hydroponic farms, water purification systems, power generation equipment, everything needed for long-term survival is installed in tunnels blasted from frozen rock. China, with characteristic scale and speed, hollows out entire mountains. The provinces of Sichuan and Guizhou, riddled with natural caves and suitable geological formations, become construction zones for massive underground facilities. Millions of workers excavate, pour concrete, install life support systems. The official purpose is listed as strategic reserve facilities, but everyone knows what they really are: last-ditch refuges for humanity's remnants if Goliath cannot be stopped. The facilities could house 100 million people, a fraction of China's population, but enough to preserve the species and rebuild civilization if the surface becomes uninhabitable. Elon Musk, now in his late 50s, but as driven as ever, accelerates Mars colonization plans. SpaceX has been launching cargo ships to Mars for years, building up supplies for a permanent colony. Now the pace intensifies. Starships leave Earth every 26 months during optimal launch windows, each one carrying 200 tons of equipment, food, construction materials, and life support supplies. The first Mars evacuation ship, specifically designed to carry 10,000 people on a one-way journey to humanity's backup planet, is assembled in Earth orbit. It's an enormous vessel, 150 meters long, built from components, launched separately, and connected like massive Lego blocks. Tickets cost $1 billion each. It's an obscene amount of money, affordable only to the ultra-wealthy. Critics call it cosmic elitism, condemning the idea that only billionaires deserve salvation while billions remain on Earth to face potential annihilation. Protests erupt outside SpaceX facilities, but the tickets sell out in 6 hours anyway. 10,000 people, the richest humans alive, secure their spots on a ship that might become humanity's Noah's Ark if Earth dies. They'll arrive on Mars after a 9-month journey, landing on a world with no breathable atmosphere, no liquid water, temperatures averaging -63 degrees Celsius, and radiation levels that would kill an unprotected human in hours. But it will be away from Earth, away from Goliath, and if Earth is destroyed, these 10,000 will be all that remains of human civilization. The Vatican announces it's digitizing every artifact and document in its archives. The Apostolic Archive, containing 2,000 years of church history, is scanned page by page, photographed in ultra-high resolution, and uploaded to servers buried 2 kilometers underground in abandoned salt mines beneath Austria. The Sistine Chapel's ceiling, Michelangelo's masterpiece, is captured in 3-dimensional scans accurate to sub-millimeter resolution. Every manuscript, every painting, every artifact in Vatican City is catalogued, photographed, and preserved digitally. If Vatican City is destroyed, if Rome is leveled, if Italian civilization is erased, at least the information will survive. The Louvre follows suit, secretly moving the most precious paintings to abandoned mines in France. The Mona Lisa, the Venus de Milo, Liberty Leading the People, masterpieces that have survived centuries of war, revolution, and upheaval, are packed in climate-controlled containers and transported to facilities where they'll be protected from impacts, tsunamis, and atmospheric catastrophe. Other museums worldwide do the same. The British Museum, the Smithsonian, the Hermitage, the National Palace Museum in Taiwan all transfer their treasures to hardened facilities. We're backing up human civilization like a hard drive we're about to drop, preserving what we can in case the original is destroyed. The preparations are practical but deeply depressing. They represent the possibility of failure, the acknowledgement that despite our best efforts, Goliath might win. But they're also necessary. Hope and preparation must proceed in parallel. We fight to deflect Goliath while simultaneously preparing for a world where deflection fails. It's the only rational approach, even if it forces us to confront our potential extinction with uncomfortable clarity. By year 5, as Goliath crosses the orbit of Jupiter and enters the region where planetary defense efforts will either succeed or fail, human society transforms in ways no sociologist predicted. The changes aren't driven by government policy or economic forces. They emerge organically from 8 billion individuals simultaneously confronting mortality on a cosmic scale. When tomorrow might not come, people reconsider what matters. The results are sometimes beautiful, sometimes chaotic, always profound. Crime drops to near zero. In cities that once struggled with robbery, assault, and theft, police departments report unprecedented quiet. Break into someone's home to steal a television? Why, when you might die in 2 years and that television will be vaporized along with everything else? Rob a bank? Money might become meaningless if civilization collapses. The usual motivations for crime, greed, desperation, revenge, lose their power when everyone faces the same cosmic threat. Even organized crime syndicates experience a crisis of purpose. A cartel boss in Mexico, responsible for decades of violence, publicly disbands his organization and donates his fortune to building survival shelters. "What's the point?" he says in a video statement that goes viral. "We were fighting over territory that might not exist." Marriage rates skyrocket. Commitment that once seemed frightening becomes appealing when time is limited. Why wait to marry someone you love? Why worry about long-term compatibility when long-term might be 24 months? Wedding venues are booked years in advance. Some couples marry within days of meeting, deciding that intensity of experience matters more than duration. The concept of starter marriages, brief first marriages, people enter in their 20s becomes normalized. If you're not sure this relationship is the one, well, maybe there isn't time to find the one, so maybe this person is enough. Paradoxically, divorce rates plummet. Couples who are contemplating separation decide to stay together. Arguments about whose turn it is to do dishes or who forgot to pay the electric bill seem absurd when measured against extinction. Marriages that were slowly crumbling find new foundation in shared crisis. Therapists report that couples who do divorce cite only the most serious grievances: abuse, infidelity, fundamental incompatibility. The petty annoyances that once ended marriages don't carry enough weight anymore. Life is too short for splitting up over dirty socks. Birth rates explode in a phenomenon demographers call the Goliath baby boom. Conventional wisdom suggested birth rates would plummet. Why bring children into a dying world? But human biology doesn't follow conventional wisdom. The biological imperative to reproduce, honed by millions of years of evolution, kicks into overdrive when species survival is threatened. Women who plan to remain childless decide they want children after all. Couples who are delaying parenthood for career reasons have babies immediately. The global birth rate, which had been declining for decades as countries developed economically, suddenly reverses. Hospitals are overwhelmed with deliveries. Maternity wards run out of space. Daycare facilities experience unprecedented demand. The babies born during these years are called the maybe generation. Maybe they'll grow up. Maybe they won't. Parents approach child-rearing differently, focusing on immediate experience rather than long-term preparation. Instead of saving for college, They take children on trips to see wonders of the world while those wonders still exist. Instead of emphasizing academic achievement, they teach children to appreciate each day. The educational system adapts. Schools eliminate standardized testing. What's the point of measuring whether children will succeed in futures that might not happen? Curriculum shifts toward practical skills, philosophical questions, and artistic expression. Children learn to grow food, build shelters, find meaning in uncertain existence. Universities make all courses free and online. Harvard, MIT, Oxford, the Sorbonne institutions that once charged tens of thousands of dollars for access open their digital doors to everyone. Why charge tuition when money might become meaningless? Professors record lectures and release them globally. Textbooks are digitized and distributed without cost. Knowledge becomes truly democratized. A teenager in rural India can access the same educational resources as a student at Cambridge. The result is no intellectual renaissance. Millions of people who previously couldn't afford higher education suddenly gain access. Enrollment in online courses explodes. People who always wanted to study philosophy, astronomy, history, or art finally get their chance. The world's religions experience both convergence and divergence. Mainstream faiths find common ground in shared mortality. The Pope, the Dalai Lama, and leading Islamic scholars issue joint statements about finding meaning in finite existence, emphasizing compassion, community, and acceptance of what cannot be changed. Interfaith services become common, with Christians, Muslims, Jews, Buddhists, and Hindus praying together in recognition that all humans face the same cosmic threat, regardless of which god they worship or don't worship. But new religions also emerge overnight, filling psychological needs the established faiths don't address. The Church of Goliath teaches that the interstellar visitor is divine judgment, punishment for humanity's hubris and environmental destruction. They preach acceptance rather than resistance. Attempting to deflect Goliath is blasphemy, interfering with cosmic justice. Their membership grows despite, or perhaps because of, this dark theology. People who feel guilty about climate change, species extinction, and environmental degradation find comfort in the idea that Goliath is deserved consequence rather than random disaster. The survivors, by contrast, believe human consciousness will transcend physical destruction. They study quantum mechanics and neuroscience, searching for evidence that consciousness exists independent of biological substrate. If Earth is destroyed but information about human thoughts, memories, and experiences somehow persists in quantum fields or information-theoretic structures, then perhaps we achieve immortality even if our bodies die. It's speculative to the point of fantasy, but it offers hope that death might not be final. Their meetings involved meditation, discussion of philosophy of mind, and attempts to upload consciousness through introspective techniques that probably don't work but provide psychological comfort. Art explodes in a renaissance that rivals 15th century Florence. Musicians compose symphonies meant to be Earth's legacy to the universe. Composers who might have spent years perfecting a single work now produce music frantically, knowing each piece might be their last. The Goliath Variations by Japanese composer Akiko Tanaka becomes humanity's anthem, a 2-hour orchestral work that moves through 7 movements, representing the 7 years of Goliath's approach. The final movement, called Maybe, is performed simultaneously by every major orchestra on Earth on the 5th anniversary of Dr. Chen's discovery. The coordination requires precise timing across time zones. As Earth rotates, the performance rolls westward Tokyo, then Moscow, then Berlin, then London, then New York, then Los Angeles, each orchestra taking up the score as the previous one finishes. The result is a continuous performance that literally circles the globe, a sonic representation of human unity in the face of cosmic threat. Writers publish their life's work unfinished, reasoning that future revision might be impossible, and it's better to release imperfect work than let it die with them. Novels appear with notes saying, "I wanted to revise chapter 12, but there's no time." Poets release collections with the caveat that these are drafts, not polished final versions, but polished versions require time we might not have. The literary world adapts, valuing authenticity and immediacy over perfection. Critics stop writing harsh reviews. Why tear down someone's artistic expression when that expression might be their last? A mysterious artist known only as Tomorrow creates massive land art visible from space. Using bulldozers, coloured sand, and thousands of volunteers, Tomorrow creates geometric patterns in turn. Deserts and salt flats, spirals, fractals, mathematical sequences. The patterns are beautiful but clearly artificial, designed to be messages for whatever intelligence might find Earth's remains if humanity is destroyed. The artist never reveals their identity, operating through anonymous intermediaries. Their work appears on 6 continents. The patterns are photographed by satellites and distributed globally, becoming symbols of hope and defiance. Humanity declaring, "We were here, we created beauty, we mattered." Mental health services, initially overwhelmed by panic and despair, evolve rapidly. Virtual reality therapy allows people to confront their cosmic anxiety in controlled environments. Patients put on VR headsets and experience simulations of Goliath's approach, impact, and aftermath. By repeatedly exposing themselves to their worst fears in safe virtual environments, they gradually desensitize, learning to function despite existential dread. It's exposure therapy applied to species-level trauma. Support groups meet in every neighborhood, every evening. These aren't therapy in the traditional sense. No professional facilitators, no structured programs. Just people gathering to talk, to share fears and hopes, to remind each other they're not alone in their terror. The groups follow a simple format. Someone shares what they're feeling, others listen without judgment, and everyone leaves knowing that 8 billion people are experiencing the same emotional journey. The phrase, "see you tomorrow," maybe replaces goodbye. It's simultaneously hopeful and realistic, acknowledging uncertainty while expressing intention to continue living. Suicide rates, after an initial spike in the weeks following Goliath's discovery, drop below pre-Goliath levels. This surprises psychologists who predicted existential despair would drive people to self-destruction. But the data is clear. Humans facing extinction together are less likely to end their lives than humans facing normal existence alone. There's something about shared mortality that creates meaning. When everyone might die, choosing to live becomes an act of solidarity rather than mere survival instinct. Depression still exists, despair still happens, but the isolation that makes mental illness unbearable diminishes when everyone acknowledges they're scared and uncertain. The most popular television show becomes Daily Earth, a 24-hour channel that just shows Earth from space. Cameras on satellites and the International Space Station before its evacuation provide continuous footage of our planet rotating against the black background of space. No narration, no music. Just Earth, blue and white and beautiful, reminding viewers what we're fighting for. The viewership exceeds 8 billion. Literally every human with access to a screen watches at least once daily. People tune in during meals, before bed, when feeling anxious. There's something deeply calming about watching Earth from orbit, seeing borders dissolve into meaningless lines on a continuous surface, watching storms swirl and continents rotate into view. The social transformation reveals something unexpected about human nature. We're not inherently selfish or violent. We're not naturally competitive to the point of mutual destruction. Those behaviors emerge from scarcity, from competition for limited resources, from misunderstandings between groups isolated by geography and language. But when faced with cosmic threat that doesn't discriminate based on nationality, race, religion, or wealth, humans default to cooperation and compassion. Crime drops because we realize stealing from each other is pointless when we're all in danger. War ends because fighting over territory makes no sense when that territory might be destroyed. Prejudice diminishes because hating people for superficial differences seems absurd when everyone faces the same cosmic fate. It's humanity's finest hour, achieved through confronting our worst nightmare. We discover we're capable of global cooperation, of prioritizing species survival over individual gain, of finding meaning in finite existence. The tragedy is that it required an interstellar mountain range threatening our extinction to teach us these lessons. If we survive Goliath, the question becomes, can we maintain this unity, this cooperation, this recognition of shared humanity, or will we slip back into old patterns once the immediate threat recedes? That's a question for the future if we have a future. For now, 8 billion souls face infinity together, and in that shared confrontation, we discover we're stronger united than we ever were divided. As Goliath approaches the Mars orbital distance in year 6, the desperate gambles humanity has been preparing for 7 years finally begin. The detection phase identified the threat. The preparation phase built the tools. Now comes the execution phase, the moment when all our technology, all our planning, all our hope gets tested against physics and probability. The stakes couldn't be higher. Success means survival. Failure means extinction. There's no middle ground. Project Hammer launches first, primarily because it requires the longest setup time. The spacecraft that departed Earth 3 years earlier have reached Apophis and successfully attached themselves to the asteroid's surface. Ion drives, powered by solar panels covering hundreds of square meters, have been firing continuously for months, gradually changing Apophis's velocity. The burns of gentle ion drives produce only a few newtons of thrust, barely enough to lift a sheet paper against Earth's gravity. But in space, where there's no friction and no air resistance, even tiny forces accumulate over time. Apophis, originally in an elliptical orbit that brought it close to Earth every 7 years, is being pushed onto a new trajectory. The destination, an interception point where Apophis and Goliath will arrive, simultaneously moving toward each other at a combined closing velocity of 78 kilometers per second. The final approach takes 3 weeks. Cameras mounted on Apophis, transmitting images back to Earth with a 20-minute light speed delay, show Goliath growing from a distant point of light into a massive irregular world. Surface features become visible craters, ridges, areas where different materials create color variations from white ice to reddish rock to dark carbon compounds. Goliath tumbles as it approaches, rotating every 17 hours and 36 minutes, different faces cycling into view. The effect is mesmerizing and terrifying, watching this ancient piece of stellar shrapnel grow larger in the cameras hour by hour. Mission controllers at the Jet Propulsion Laboratory in Pasadena monitor Apophis's trajectory with obsessive precision. Small correction burns adjust the asteroid's path, compensating for solar wind pressure, accounting for outgassing from Goliath that slightly alters its trajectory, refining the impact point as new data arrives. The last correction burn happens 6 hours before impact. After that, Apophis is committed. Its trajectory is ballistic, unchangeable, the final vector locked in. Either the calculations are correct and impact occurs, or there's been an error and 7 years of work fail in the final moments. Impact happens at 11:37 Universal Time on a Tuesday. 8 billion people watch live feeds, holding their breath, waiting. The cameras on Apophis show Goliath filling the entire field of view, surface details visible in extraordinary clarity. Then, in an instant too fast for human perception, the image whites out. The impact converts kinetic energy to heat so rapidly that both Apophis and a portion of Goliath's surface vaporize instantly. Rock and ice transform directly to plasma, temperatures exceeding 100,000 degrees Celsius, creating a fireball that expands at thousands of kilometers per second. For 17 minutes, Goliath glows brighter than Venus as seen from Earth. Astronomers with telescopes pointed at the impact coordinates measure an energy release equivalent to 4 billion tons of TNT, roughly 80,000 times the Hiroshima bomb, all released in less than a second. The flash is visible to the naked eye from Earth, a sudden bright point appearing in the pre-dawn sky, fading gradually over the next hour as the vaporized material expands and cools. When the light fades and telescopes can observe again, the results are simultaneously encouraging and sobering. Apophis created a new crater on Goliath's surface 12 kilometers across, 3 kilometers deep, exposing material from Goliath's interior that has never seen sunlight. Spectroscopic analysis of the ejecta reveals more unusual isotope ratios, confirming Goliath's supernova origin. But more importantly, the impact changed Goliath's trajectory. Radar measurements tracking Goliath's position before and after impact show a deflection of 0.003 degrees, 0.003 of a degree. It sounds negligible, but at interstellar distances, tiny angles create enormous position differences. That deflection, if nothing else changes, moves Goliath's predicted Earth impact point by roughly 80,000 kilometers. Not enough to guarantee safety, but enough to shift probabilities significantly. The success of Project Hammer energizes humanity and validates the multi-method approach. If one method achieves measurable deflection, perhaps the combined effects of all methods will be sufficient. Project Mirror activates next, and the spectacle is extraordinary. 10,000 satellites, positioned in a carefully calculated formation, extending across millions of cubic kilometers of space, orient their 50-meter reflective surfaces simultaneously. From Earth, the satellite swarm is invisible to the naked eye. Each individual satellite is too small and too far away, but radio telescopes tracking their positions confirm the formation is stable, the mirrors aligned correctly, the focusing geometry optimal. Controllers transmit the activation command, and the mirrors tilt to their operational angles. Concentrated sunlight, gathered from across the enormous collection area of 10,000 mirrors and focused onto a point 30 kilometers across on Goliath's surface, raises the surface temperature by 300 degrees Celsius. Water ice, which normally sublimates slowly in the weak sunlight this far from the sun, now boils explosively. Methane ice, even more volatile, transitions directly from solid to gas in violent bursts. The gas jets create thrust, not much thrust per individual jet, but Goliath's entire sunlit hemisphere is now a rocket engine with thousands of nozzles firing simultaneously. The outgassing continues for 4 months, as Project Mirror maintains its focus. Goliath's rotation means different surface areas cycle through the heating zone, but the total thrust averages to roughly 10,000 newtons, equivalent to a large rocket engine firing continuously. It doesn't sound like much compared to Goliath's enormous mass, but force applied over months generates significant velocity change. Telemetry data shows Goliath's trajectory shifting, the rate of deflection increasing week by week. By the time Project Mirror completes its planned operation, the satellite's running low on station-keeping fuel, unable to maintain formation any longer, the total deflection reaches 0.007 degrees. Combined with Project Hammer's contribution, Goliath has now been deflected by 0.01 degrees, 1/100th of a degree. Still not enough, but the probability of Earth impact has dropped from 78% to 42%. We're winning, but we haven't won yet. Project SAR begins when Goliath crosses the orbit of Mars. The Russian nuclear devices, positioned months earlier along Goliath's predicted path, detonate in sequence. Each explosion creates a sphere of plasma and debris expanding at thousands of kilometers per second. The spheres overlap, creating a cloud of material stretching across millions of kilometers. Goliath plows through this cloud like a ship through fog, and while each individual particle impact is negligible, there are trillions of particles. The cumulative effect resembles atmospheric drag, friction slowing Goliath incrementally. The nuclear explosions are visible from Earth, brief flashes of light in the darkness between Mars and Earth. Some people celebrate, interpreting each flash as a blow struck against the cosmic intruder. Others protest, arguing that detonating nuclear weapons in space, even for planetary defense, normalizes nuclear warfare and risks escalation. The debate seems absurd to many. We're facing extinction, and people are worried about the philosophical implications of nuclear weapons in space. But the debate reflects genuine moral concerns about what methods we're willing to use for survival and what principles we're willing to sacrifice. The final nuclear device detonates 3 days before Goliath's closest approach to Earth. Telemetry confirms deflection of 0.004 degrees less than Project Mirror, but still significant. Total deflection now stands at 0.014 degrees. Probability of Earth impact? 17%. We're almost there, but 17% is still terrifyingly high. 1 chance in 6 that everything ends. Russian roulette with a revolver pointed at planetary civilization. Project Dragon, China's secret contribution, activates in the final week. While the world focused on Projects Hammer, Mirror and SAR, China was building a mass driver on the Moon, an electromagnetic catapult capable of launching payloads at high velocity. The construction happened away from Earth's observation, on the lunar far side, hidden from casual, telescopic scrutiny. The mass driver is 50 kilometers long, built from components manufactured in lunar regolith processing facilities that extracted metals and silicon from moon rocks. It operates on solar power, capacitor banks storing energy that's released in powerful electromagnetic pulses that accelerate payloads down the launcher. For 6 months, the mass driver has been launching lunar regolith at Goliath. Not refined metals or manufactured projectiles, just dirt. Raw lunar soil scooped up by automated mining equipment and packed into canisters. Each canister weighs 5 tons and launches at 20 kilometers per second. The mass driver fires every 90 minutes, the recharge time needed to store sufficient energy for the next shot. Do the math. 16 shots per day, 5 tons per shot, 6 months of operation. China has hurled roughly 14,400 tons of moon dust at Goliath. The projectiles arrive as a sparse stream, one every 90 minutes, each impact releasing kinetic energy equivalent to a large conventional bomb. Individually, they're insignificant, but accumulated over months, the millions of tiny impacts create measurable deflection through the same principle as Project SAR friction applied over time. The exact deflection is difficult to measure because it's so small, but statistical analysis of trajectory data before and after Project Dragon's operation suggests approximately 0.002 degrees of deflection. Total deflection from all methods combined, 0.016 degrees, 16 thousandths of a degree. Probability of Earth impact, 4%. It's enough. The numbers say we'll survive. Goliath will pass close, very close, but it will miss. The final trajectory calculations, refined continuously as Goliath approaches and measurement accuracy improves, converge on a closest approach distance of 400,000 kilometers, roughly the distance to the Moon, close enough that Goliath will be the dominant object in the night sky for 12 hours during closest approach, close enough that gravitational effects will trigger earthquakes and tsunamis, close enough that we'll remember this for the rest of human history, but not close enough to hit us directly, not close enough to sterilize the planet. As Goliath makes its final approach, the entire night sky fills with a sight no human eyes have ever witnessed. The object is visible to the naked eye weeks before closest approach, first as a bright star, then as a disk that grows nightly. By the final week, Goliath subtends an angular size larger than the Moon. Surface features are visible without telescopes: craters, ridges, the massive impact scar left by Apophis, areas where Project Mira's heating created outgassing plains. The object tumbles as it approaches, rotating every 17 hours and 36 minutes, giving Earth's population a complete view of this interstellar wanderer that almost killed us. During the 12 hours of closest approach, Goliath dominates the sky. It's not a distant object anymore. It's right there, a world-sized mass hanging overhead, close enough to see mountains and valleys in ordinary binoculars. The visual effect is overwhelming, triggering instinctive terror in millions of people who know intellectually that impact has been avoided, but whose primate brains scream danger at the sight of something so massive so close. Some people can't look at it, hiding indoors with curtains drawn. Others can't look away, transfixed by the cosmic spectacle, watching an alien world pass by just outside our orbital neighborhood. Earth experiences 12 hours of intense gravitational disruption. Tides rise 5 meters higher than normal as Goliath's gravity pulls on Earth's oceans. Coastal cities evacuated days earlier watch as seawater surges through empty streets. The tidal forces aren't strong enough to cause catastrophic damage to intact structures, but anything loosely secured is swept away. Boats tear from moorings, cars float down boulevards. Debris accumulates in enormous piles as the tides recede. Earthquakes strike globally, though most are moderate in intensity. The gravitational tidal forces stress Earth's crust, triggering slippage along fault lines that were already near their breaking point. California experiences a magnitude 6.8 earthquake along the San Andreas Fault. Japan, accustomed to seismic activity, weathers multiple quakes ranging from magnitude 5 to 6.2. The Himalayan region, where tectonic plates collide and geological stress accumulates constantly, releases energy in a magnitude 7.1 event that triggers avalanches, but causes minimal casualties due to mandatory evacuations enforced weeks earlier. Volcanic eruptions increase globally as magma chambers stressed by tidal forces find release through existing weaknesses. Iceland, sitting on the mid-Atlantic ridge where tectonic plates diverge, sees multiple volcanoes activate simultaneously. Italy's Mount Etna, already one of the world's most active volcanoes, increases its output dramatically. In Indonesia, volcanoes throughout the archipelago erupt in a coordinated display that would be scientifically fascinating under other circumstances, but now just adds to the catalogue of Goliath-induced disasters. The Moon's orbit, stable for billions of years, shifts slightly. Goliath's gravitational influence pulls on the Moon as well as Earth, creating complex three-body dynamics. The Moon moves into a slightly more elliptical orbit, changing Earth's tides permanently. The effects are small. Tides will vary by perhaps 10 to 15 centimeters compared to pre-Goliath patterns, but they're permanent. Future generations will measure tides differently, calibrating coastal infrastructure for a new tidal regime. And then, after 12 hours that feel like 12 years, Goliath passes. The massive object moves beyond Earth, heading toward the inner solar system, gradually shrinking in the sky as its enormous velocity carries it away from us. It will round the sun, using solar gravity to change direction and head back out toward interstellar space. In several decades, Goliath will cross the orbit of Neptune outbound, leaving our solar system, continuing its lonely journey through the galaxy. Perhaps in a few million years, it will encounter another star system. Perhaps it will threaten other worlds where other intelligent beings watch it approach and struggle to survive. Or perhaps it will wander forever, a cosmic wanderer carrying materials forged in stellar death, drifting through the eternal dark between stars. The aftermath assessment takes months. 2,100,000,000 people died from Goliath-related disasters. Most deaths occurred in coastal regions from tsunamis and tidal flooding. Others died in earthquakes and building collapses. Some died in the evacuations themselves, traffic accidents, medical emergencies in overcrowded shelters, violence that erupted when resources became scarce. 2 billion is a number almost too large to comprehend, representing more deaths than all wars in human history combined. Each one is a tragedy, a life ended, families destroyed, potential unrealized. But 6 billion survived. The human species continues, civilization endures, knowledge persists. The technological and scientific achievements developed to fight Goliath, the detection networks, the deflection methods, the international cooperation frameworks remain intact and available for future threats. We proved we can face cosmic danger and survive through ingenuity, determination, and cooperation. The recovery takes years. Coastal cities are rebuilt, incorporating lessons learned about tidal forces and ocean dynamics. Agricultural production, disrupted by climate effects from volcanic eruptions and the psychological trauma of the maybe generation, gradually returns to pre-Goliath levels. The global economy, which contracted 37% during the crisis years, slowly recovers as normal commerce resumes and people begin planning for futures they once doubted would exist. The technologies developed for deflection revolutionized space travel. Within a decade, humans walk on Europa, drilling through the cracked ice to explore the ocean where organic molecules suggest life might exist. The ion drive technology, perfected for moving Apophis, enables missions to the outer solar system with unprecedented speed. The first crewed mission to Titan, Saturn's largest moon, launches just 15 years after Goliath's passage. The mass driver on the moon becomes the foundation for a permanent lunar colony, using electromagnetic launch to send materials to Earth orbit at costs far lower than rocket launch. The global cooperation framework created to fight Goliath transforms into Earth's first truly planetary government. Not immediately, national sovereignty persists, and countries maintain their identities and cultures, but the United Nations is reformed into an organization with actual authority over existential threats. The Planetary Defense Coordination Committee becomes permanent, with funding guaranteed by treaty and enforcement mechanisms that ensure all space-capable nations contribute to monitoring and response capabilities. No future asteroid or comet will catch us unprepared. We're watching now, continuously, with eyes that never close. Children who lived through the Goliath crisis, the maybe generation, grow up with fundamentally different worldviews than their parents. They experienced existential threat during their formative years and emerged understanding that humanity is simultaneously vulnerable and capable, fragile and resilient. As they enter adulthood, they bring this perspective to politics, science, art, and philosophy. They're less interested in abstract debates about national borders and more focused on practical questions about species survival. They're less concerned with accumulating wealth and more interested in creating meaningful experiences. They're the first truly planetary generation, raised during years when humanity acted as one species rather than competing nations. Goliath becomes a holiday, observed annually on October 15th at 3:17 a.m. Hawaii Standard Time, the moment Dr. Sarah Chen first detected the object that almost killed us. It's not a celebration exactly, more a remembrance of vulnerability and resilience. Every year, billions of people step outside at that precise moment, wherever they are on Earth, and look up at the stars. They remember the night everything changed. They honor the 2 billion who didn't survive. They reaffirm commitment to planetary defense and global cooperation. And they remind themselves that the universe is dangerous, that threats we can barely imagine might be heading toward us right now, but that we're not helpless. We see, we measure, we calculate, we fight, we survive. Dr. Sarah Chen, now in her 60s, speaks at the 15th anniversary commemoration. She's been speaking at these events every year, reluctant celebrity status thrust upon her for discovering the threat. She usually keeps her remarks brief, uncomfortable with attention, but on this anniversary, she speaks longer than usual, and her words become the definitive statement of what Goliath meant and means. "I think about that night often," she says, standing before a crowd of thousands in Hawaii, millions watching worldwide. "I think about the coffee mug that slipped from my fingers when I realized what I was seeing. I never did clean up those ceramic shards properly. The janitors found them in the morning. Such a small thing, a broken mug, but it marks the moment my life changed and, I suppose, when all our lives changed. We learned we're not safe. We learned the universe doesn't care about us. But we also learned we're not helpless. When faced with cosmic threat, we didn't panic or despair or give up. We measured, we calculated, we cooperated. We built tools and implemented plans and changed the trajectory of a mountain-sized object moving at 42 kilometers per second. That's remarkable. That's something to remember when we look up at the stars. They're beautiful, they're dangerous, and we're capable of surviving among them. The last line of children's history books, standardized globally through the new educational frameworks, reads simply, "Goliath came, Goliath passed, we remain." It's become a cultural touchstone, a reminder that threats can be overcome, that human ingenuity and cooperation can face seemingly impossible challenges. Parents quote it to children when teaching about resilience. Politicians invoke it when arguing for continued space program funding. Scientists reference it when proposing bold new missions. But perhaps more importantly, it's a warning. Goliath was detected 7 years before potential impact. 7 years to prepare, to build, to cooperate, to act. What if the next threat gives us less time? What if something approaching even faster, from an angle we're not watching, appears with only months or weeks of warning? The detection networks scan continuously now, our vigilance maintained by international treaty and sustained funding. But the universe is vast and dark, and threats might approach from any direction. We're watching, but we can't watch everywhere simultaneously. So we build redundancy into planetary defense systems. We maintain the technologies developed during the Goliath crisis. We fund research into deflection methods. We cooperate internationally, recognizing that cosmic threats don't respect borders. We plan for scenarios worse than Goliath, hoping we never face them, but preparing anyway. And every October 15th, at 3:17 a.m. Hawaii time, we remember the Night Doctor. Sarah Chen saw death coming from 13 billion kilometers away, and humanity decided that death would have to go around us rather than through us. We're still here, we're watching, and if the universe sends another visitor, we'll be ready.